In this unit, we're going to explore a number of applications of derivatives again, but in a new context, looking at how to generate graphs for a whole family of related functions. We're going to see connections with that to what are called Taylor polynomials, which are extensions of tangent lines. And finally, we're going to look at a traditional calculus topic called L'Hopital's rule. All of those different areas are going to involve interpreting first and second derivatives. So what we're going to do first is explore what we can learn again from first and second derivative information. We've seen already that if a derivative is positive at a point, we would say the function is increasing. If the derivative is negative, then a function is decreasing. So that's what we've seen before. And decreasing functions would all have negative slope values, so negative first derivatives. We haven't talked much about second derivatives yet, but we can make some conclusions about the shape of a graph based on the second derivative. A graph that's concave up has derivatives that are negative but getting bigger, and that would translate to the second derivative, or the rate of change of the first derivative, being positive. And that can be as simple as this part of an always decreasing function being concave up, the whole, or just positive concave up, or the full U shape. All three of these graphs have a concave up shape. And likewise, we can have concave down appear in a number of different forms, sometimes just increasing and slowing down, sometimes decreasing and going faster, and then sometimes a full U shape. One technical feature we're going to bring up in more detail in an example is that we're going to get more specific about the interval. So this notation here with the round brackets indicates an open interval, and that means that the endpoints are excluded. However, if the function's actually defined on the closed interval around it, then this would be a closed interval. And we'll see how that plays out. It's a fairly minor technical point, but it's worth exploring just to see what the consequences are to something that comes up that's a little counterintuitive. All right, so first derivative can tell us increasing versus decreasing. Second derivative can tell us concavity of a function. Of course, those were all the positive values. What about when the derivative is 0, or where the second derivative is 0? Well, we've seen examples before where the first derivative is 0. Those are any points where the tangent line slope will be exactly 0. And it can occur at a min or a max, or an inflection point. This is f prime equals 0, min, max, or inflection point. Now the second derivative equals 0 can happen most commonly at a transition between concavity. So here we have concave up. On this side of this point, it's concave down. And in between the two, if we think of continuous functions and what we studied earlier in the course, concave up means the second derivative is positive, concave down means the second derivative is negative. In between, if the second derivative is continuous, it must pass through 0. So we have positive second derivative, negative second derivative, and at that transition point, we must have the second derivative equal to 0 to go between those two values. And that can, of course, look the same way with concave down, then to concave up. And notice the slope at the transition doesn't have to be 0. That's a nice special case for the first derivative being 0, but points of inflection don't have to have that all the time. So these two cases here, points of inflection, are simply points where the second derivative equals 0. And it's possible, though less common, to have something where it's concave down and then it straightens out. And again, if something straightens out, that means the slope is constant. That means the second derivative would be 0. and then it goes back to concave down again. So if a graph ever straightens out for a brief instant in between two stretches of concave down, you would also have second derivative equal to 0 because the slope is not changing. Just as when the first derivative equals 0, it's a point where the function is not changing or is briefly constant. Here we would have the slope being briefly constant. Now just a brief note on the idea of the intervals of increasing and decreasing. Let's take a look at the function f of x equals x squared and find the derivative. Well, that's our easiest derivative ever, except for a constant. F prime of x will be equal to 2x. Now where is that derivative greater than 0? Well, I think we can all see that at x equals 0, the derivative equals 0. So if we look at the signs here, and we talk about the sine of f prime, which is 2x, we're going to get positive values all the way up past 0. Anything larger than 0 is going to give us a positive derivative, because 2 times a positive number is positive. And anything where x is negative, any points where x is negative will give a negative first derivative. So these would be the open intervals. So negative infinity up to 0, but not including 0, and 0 up to positive infinity is where the slope is positive. So we have the open intervals we talked about with the slope being positive or negative. And let's see what the conclusion of that is. Describe the intervals on which we would say f of x is increasing. Well, we said f prime of x is positive for, let's do it that way, x being on the interval from 0 to infinity. We would say that f of x is increasing on the interval 0 to positive infinity again, but including 0. Including that endpoint now. Now, does that make any sense? I think if we look at the graph of x squared, we would say, yes, that does make sense. If I were to ask, including 0, if I start at 0 and I pick any point later on, the function goes higher. Even if I take the smallest possible step away from 0, I'm going to go up. The function value is going to increase. And so it's pretty comfortable to say that the function is going to be increasing on the interval from 0 to infinity. Likewise, we could say that the function is decreasing on the interval 0 down to negative infinity. So decreasing here and increasing on the other interval, so square brackets. Okay. F prime of x less than 0 on negative infinity to 0, and so decreasing on negative infinity all the way into and including 0. And the minor counterintuitive thing is that the point 0 is included in both intervals. Now, does that mean the function's increasing and decreasing at that point? No. Increasing and decreasing only really makes sense if we compare 2 points. Increasing means if I take any step to the right, I get a larger value of the function. And so, including 0 and comparing it to any points on the right, I will definitely go up. If I take any point on the left and compare it to 0, 0 will always give me a lower point. So we can still say quite reasonably and consistently that the function is decreasing on if I compare any 2 points from negative infinity up to 0 and including 0. The 0 point will always be the lowest. And likewise on this interval, 0 will always be the lowest, and then it increases afterwards. But it just takes a little bit of thinking about what we really mean, and it returns the focus to technical definitions. What do we really mean by increasing on an interval? Again, this is a fairly minor technical point, but one that illustrates some of the peculiarities that arise when we look at specific definitions. It won't be a major focus of the course, though.